This is section 2.4 on exact equations. Let f of xy, I'm going to pen out, let f of xy equal c for some constant c. So note that f is a multivariable function in this instance. So we're going to start taking some partial derivatives. If you wanted to take the derivative with respect to x of fxy, it is actually going to take this form. And I'll leave it as an exercise for you to see that yourself. If you were to take the implicit derivative of some multivariable function, this is how you would solve it. Now, the right side of the equation, c was a constant, so that's just equal to 0. So we can manipulate it as such to isolate what dy dx is equal to. It's equal to the partial derivative of f with respect to x divided by the partial derivative of f with respect to y. Now, when we isolate df, we get that df is equal to the differential or the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y times dy. Now, the reason we've done this is for similar reasons in the last video why we were talking about the product rule. The product rule was an equation that we had that told us something about, it was an equation involving a derivative, which is, exactly what we're talking about, differential equations. F prime g plus g prime f. That's just a tool that we can use when we're trying to evaluate differential equations. Well, this is another one because df is the derivative of f. So this is something that will help us in a similar way. If we can make one side of an equation look like this, then we will know that it's actually the derivative of a multivariable function. Yeah, here previously with linear equations, we tried to make one side of the equation look like the result of a product rule to simplify an integration. Now we will try to make the one side of the equation look like a total differential, which is what we call this, the total differential. So let's use this to solve the differential equation 3x squared y squared dx plus 2yx cubed dy is equal to 0. So this equation is in the form of a total differential where f is equal to x cubed y squared. So we can actually check that. So if f is equal to x cubed y squared, then df dx, well, that's just the derivative with respect to x, imagining that y is just a constant. So that will be 3x squared y squared. And the derivative of f with respect to y, partial derivative. Again, that's just the derivative of with respect to y. So imagining that x is a constant. So x cubed is just going to remain the same. So we get 2x cubed y. And that's exactly what we have. 3x squared y squared dx plus 2x cubed y dy equals 0. So the left side of this equation is actually the derivative of a multivariable function. It's like we took implicit differentiation of x cubed y squared. That's what we would reach. So moving backwards, taking the integral, we can get that f of xy is equal to x cubed y squared. So that's exactly what we've done here. We've said the left side of the equation is just the derivative of x cubed y squared. So if we integrate both sides of the equation, we get x cubed y squared on the left, and the right was just 0. So now it's just constant c. Now this is an implicit solution, but it can be made explicit if we isolate the y, and y would be equal to plus or minus the square root of c over x cubed. So here's the definition that falls out of that. The differential form m of xy, so m is some multivariable function, times dx, plus n of xy, where n is another multivariable function, times dy, is said to be exact if there is a function such that m represents the partial derivative of f with respect to x, and n represents the partial derivative of f with respect to y. You'll notice that that's exactly what we've done up here. We noticed that the partial derivative of f with respect to x was multiplied by dx, and the partial derivative of f with respect to y was multiplied by dy. We're giving them different names, m and n, but it's the same thing. If that is the case, and those do represent those partial derivatives, then we say that mxy dx plus nxy dy equals 0 is an exact equation. So we can skim past some of this stuff, but I'll point out the important stuff. You can read this on your own. We get this little rule that falls out. If the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, then we know that it is exact. We'll do a teensy little proof for that. So remember that m, let's see right here, m is equal to delta f delta x, and n is equal to delta f delta y. So why would this statement be true? Well, let's take m and take its partial derivative with respect to y. So dm delta m delta y is equal to then we'll do the same for n. And we reach the same thing. So that's why we get this compatibility condition, where if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, then we have that m is equal to delta f delta x, n is equal to delta f delta y, and we have an exact equation. That is something that does represent a total differential that can be easily integrated. So with all that, how do we actually use it? Here's our method for solving exact equations. If m dx plus n dy is equal to 0 is exact, then the first thing we know is that delta f delta x equals m. That's nothing new, that's just restating this. We're going to take that equation and we're going to integrate it with respect to x. So if you integrate delta f delta x with respect to x, you're just left with f of xy. And then if you integrate m, you get the integral of m. So nothing new here, but I will explain where this gy comes from. Since this is a partial derivative and we're integrating with respect to x, this multivariable function, instead of just putting c here as a constant, we need to recognize that the only variable we're integrating with respect to is x. So all other variables need to be treated as constants. So this isn't just simply some constant, it's literally any function of y, because as far as we're concerned, y is a constant because we're integrating with respect to x. So I'll skip these steps. You can read them on your own time, and we'll actually try to start solving here because we definitely have enough information to get to work. So we have 3 sine y x squared dx is equal to negative cos y x cubed plus y squared dy. First question is it exact? Well, when we're checking exactness, we take dm dy and we compare it to dn dx. So the derivative of 3 sine y x squared with respect to y is 3 cos y x squared. Right there. And the derivative of negative cos yx cubed plus y squared with respect to, oh, sorry, I skipped a step here. The equal sign is actually in the wrong spot. We're used to being m dx plus n dy is equal to 0. So of course the first step, let me erase some of this. The first step was to move this to the left side of the equation. And that's how we get to here. So now we have m dx plus n dy equals 0. Okay, we've already calculated this derivative of m and it worked out. Now let's calculate this derivative of n. Well, we're doing it with respect to x, so that y squared is actually just going to fall off. And the derivative of cos yx cubed with respect to x, well, that 3 is just going to come down front and reduce to a 2. So we get 3 cos yx squared. So these do, in fact, end up being equal, which is perfect. So we can say that it is exact. So if it is exact, that means that we have enough information to calculate f. So recall that the partial derivative of f with respect to x is equal to m, and the partial derivative of f with respect to y is equal to n. These are the two equations that we're going to have to keep making use of to get to the end here. So we start by using our delta f delta x is equal to mxy, and we're going to integrate both sides of that equation, as we spoke of earlier. So now we know what f of xy is equal to. It is equal to the integral of m with respect to x plus some function of y. Well, m, as stated above, is 3 sine y x squared. So we plug that in, but now we need to take its integral with respect to x. So when you integrate with respect to x, you get to act like all of the y terms are constant. So all we're worried about is this x squared and the 3. So it becomes sine y x cubed plus whatever this function of y is going to be, gy. So note that we're almost done. F of xy is what we're trying to solve for, the original equation. And we know that it's equal to sine of y times x cubed plus some function of y. So now we just need to solve for what g of y is. We got this far just by using delta f delta x equals m. Now we're going to make use of delta f delta y equals n. So we have this equation, f of xy is equal to sine yx cubed plus gy, and we want to put it into this form so we can make use of this. So we're going to need to take the partial derivative with respect to y of both sides of this equation. So that's how we get to the first step here. We take the partial derivative of both sides, so we get delta f delta y is equal to delta delta y of this whole right side. Now, delta f delta y is equal to n, so that's an easy substitution. But what happens to the right side? Well, I'm going to take the derivative term by term with respect to y. So this sine y x cubed, the x cubed, we get to just act like that's some constant. So we get x cubed cos y. And the derivative of gy with respect to y is g prime of y. Now, we're going to do a substitution because we actually know what n is equal to. We're going to have to scroll up a little bit, but we see that n is equal to, let me erase some of this so it's more clear. N is equal to this, cos y x cubed plus y squared. So that's why we plug in cos y x cubed plus y squared on the left side where n is. And on the right side, we still have x cubed cos y plus g prime of y. Well, let's cancel out the like terms. And we get that y squared is equal to g prime of y. So g of y is the integral, which is 1 over 3y cubed plus c. So therefore, we can plug this in to our f equation, and we have a final answer. Therefore, f of xy is equal to sine yx cubed plus 1 over 3y cubed plus c. Therefore, let's go back to our original equation. We know that sine yx cubed plus 1 over 3 y cubed plus c, which is just f of xy, equals d, is the solution, where c and d are both constants. We can simplify by combining c and d into a new constant. So it's just sine yx cubed plus 1 over 3y cubed is equal to b. Let's look at another example. Solve x plus x squared y plus y to the 4 dx plus 1 over 3x cubed plus 4y cubed x plus 4y dy equals 0. Step 1, is it exact? So we're going to take the derivative of the first term with respect to y, and we're going to compare it to the derivative of the second term with respect to x. And lo and behold, we get that they are equal, x cubed plus 4y cubed. That's the only criteria we need. We know that this is an exact equation now. So now we just need to calculate f, and we're going to use the exact same method before. We're going to make use of our two facts, that delta f delta x equals m, and that delta f delta y equals m. We'll start with m for no particular reason. So by integrating both with respect to x, we isolate f. Then we plug in our m value. These are the exact same steps as before. We integrate with respect to x. So that is, remember that the y terms are just mostly going to stay the same because they're just constants in this instance. It's the x's that we're integrating with respect to. So we get that this is what f is equal to. But there is a gy there. So that's what we're going to need to determine. And that's why we're going to use this equation. N is equal to delta f delta y. So we're going to take the derivative of both sides with respect to y, partial derivative. So that's how we get our delta f delta y, which turns into n. On the right side, we're going to, term by term, take the derivative of this with respect to y. So note that this term doesn't have any y's in it, so it's like a constant. It's just gone. It disappears upon derivative. 1 over 3x cubed y just becomes 1 over 3x cubed. X, y to the 4, that 4 is going to come down front and reduce to a 3, so we get 4y cubed x. And the derivative of g with respect to y is just g prime of y. Now, we get to substitute in n's value, and we'll just scroll up to see this is what n is equal to from the question. 1 over 3x cubed plus 4y cubed x plus 4y. So we just plug that in. And now we'll just get rid of the common terms, 1 over 3x cubed, 4y cubed x, and we're left with 4y equals g prime y. We'll take the integral of both sides, and we get 2y squared plus c is equal to gy. Therefore, f of xy is equal to, let's find it here. It's this, but we now know what gy is equal to. Gy is equal to 2y plus c. So we're going to combine it all together. And we're going to get f of xy equals 1/2 x squared plus 1 over 3x cubed y plus xy to the 4 plus 2y squared plus c. Thus, if we set that equal to a constant, we get a solution where c and d are constants. And we can simplify by combining c and d into a new constant called b. When solving with this method, we will always have this final step of combining the two constants. This can be streamlined by ignoring the constant value in the integration of g prime of y altogether. I'll explain what that means. I have been always showing this constant c, but since we always in the end just end up subtracting it and renaming it, we don't actually have to do that step.